Every society has grand, overarching ambitions for its citizens. The central challenge of teaching is taking those massive, abstract ideas and funneling them down into concrete, observable results inside a single classroom. We start with educational objectives. These are broad, philosophical, and flexible goals. They are built on the overarching needs of society, things like developing good citizens or fostering scientific literacy. Compare that to instructional objectives. These are narrow, highly specific, driven by psychology, and focus strictly on behavior we can measure right now. Educational theorists DeSecco and Crawford defined an instructional objective as the precise, immediate, and observable behavior a teacher expects from a learner by the end of a session. This framework converts macro-philosophical intent into micro-psychological, observable data. To bridge the gap between those massive societal goals and a daily lesson, educators rely on a rigid structural pathway to drill down from the macro to the micro. This diagram illustrates the NCERT hierarchy. Broad educational objectives step down into level objectives. These isolate into subject objectives, like history, which narrow into unit objectives, and finally arrive at the foundation, a precise, observable lesson unit. To accurately classify and measure the exact outcomes expected at this final lesson level, educators use an overarching framework known as the Revised Bloom's Taxonomy, which maps learning across 3 distinct domains. This cascade provides the specific metrics required to determine if a 45-minute lesson actually aligns with its parent societal goal. There is a persistent misconception that cognitive learning is a simple linear ladder. In reality, it is a complex 2-dimensional matrix. Look at this grid. The first dimension is the knowledge domain, represented here on the vertical z-axis. This axis categorizes the exact type of information a learner is acquiring. The foundational step is factual knowledge, dealing purely with basic terminology, isolated definitions, and specific details. One step up is conceptual knowledge. Here, isolated facts are connected to form broader theories, classifications, and structural models. Next is procedural knowledge. This is the mastery of subject-specific algorithms and methods, knowing the strict criteria for how to execute a specific task. At the apex of this axis sits metacognitive knowledge. True mastery requires the learner to achieve strategic self-awareness and maintain confidence regarding their own cognitive processes. The second dimension extends out along the x-axis, the cognitive process domain. This dictates exactly how the learner interacts with the knowledge they've acquired. This axis tracks progression from simple remembering and understanding, advancing outward into analyzing, evaluating, and ultimately creating entirely new patterns. To see how this matrix functions in practice, we can focus specifically on the intermediate application stage of the process. Take Archimedes' principle of buoyancy as a classic test case for applying conceptual knowledge to a new situation. In this scenario, a student must take their understanding of displacement and apply it to explain a specific phenomenon, why a tiny, lightweight metal needle sinks to the bottom of a glass of water. The second half of the application requires the student to independently explain the reverse, why a massive, incredibly heavy steel ship remains afloat on the ocean. Successfully answering both scenarios proves the student has hit a specific coordinate on our matrix. They have moved past rote memorization and demonstrated functional, adaptable understanding. But mental processing is only one part of the learner. We also have to map their internal emotional and attitudinal landscape, actively adopting a scientific perspective over superstition. At the organization stage, the learner resolves internal moral conflicts and builds a cohesive value system. The final tier is characterization. Here, isolated values transition into a total life philosophy that permanently controls behavior. Lessons heavily skewed toward the cognitive domain without addressing the affective domain produce individuals who possess factual power but lack an ethical framework. The third and final architecture is the psychomotor domain. This exclusively governs physical movement, coordination, and manual skill execution. Following educational researcher Elizabeth Simpson's 7-stage model, this domain starts with basic sensory perception and set, which is the physical and mental readiness to act. The learner then progresses through guided response, learning via imitation and trial and error, until they reach mechanism, the point where the physical action becomes a reliable habit. Next is complex overt response. This requires executing highly coordinated sequences. Think of a learner manipulating a computer mouse and keyboard simultaneously to generate complex digital art. The apex stages are adaptation and origination. The learner now possesses enough physical mastery to modify old skills for new problems or invent entirely new physical techniques. Physical mastery follows a highly structured taxonomy, requiring deliberate, sequenced instructional engineering to achieve. When we pull back to view all three architectures operating simultaneously, we see the true complexity of a human learner. A true instructional objective does not exist in a vacuum. A robust pedagogical strategy must intentionally target specific coordinates across the cognitive, affective, and psychomotor domains at the exact same time. Building this unified profile is the only way for educators to accurately assess and evaluate a learner's actual capability. Teaching a single fact without addressing its emotional weight or its physical application creates an incomplete, fractured educational experience. This complex theoretical data must translate directly to the teacher's primary daily tool, the lesson plan. As outlined by the educational theorist Norman Gronlund, it is only these precisely stated instructional objectives that can dictate a teacher's choice of content, teaching aids, and evaluation methods. Effective instruction relies on a rigorous, pre-planned scientific process. Without these precise objectives, the classroom experience can lack direction and efficiency. Educators act as engineers, deliberately designing and executing observable, measurable changes across human cognition, values, and physical capability.